Okay, so let's start. Um, so in the last few the classes so far, we covered the basics of what is required in multivariable calculus and linear algebra. And today onwards, we'll start with the main content, which starts with convex sets. Right. So this course will be about convex optimization problems and what we can learn about solving general optimization problems from just convex optimization problems, right? So as we'll see, convex optimization problems have a special structure. Um, so the notion of convexity is useful beyond just optimization. It's useful in mathematics, physics, electrical engineering, and so on. So we'll begin with some basic notions of convex sets. So this course will be inherently very geometrical. There's a lot of intuition to be gained by viewing the geometry of convex sets and convex functions, because it will eventually let us design algorithms and understand why algorithms behave the way they behave, why it is possible to solve certain kinds of optimization problems easily, whereas it's difficult to solve more general optimization problems in an efficient manner. Okay, so we'll start with some very basic concepts. And the first concept that we'll start with, again, we're always going to be dealing with, at least for most part, we'll be dealing with subsets of Rn. Right? So Euclidean space is going to be the focus for most of our course, but we'll also see how the intuition that we gain from Rn can be used for more general sets and more general problems. Right. So we'll start first by defining what a line is in Rn. Right. So what does a line look like? So analytically, a line is essentially a set. It's a set of, like, you know what a line is in 2 dimensions and 3 dimensions. You can visualize it. So a line is simply the set of all points x that let's take a line that passes through 2 points x1 and x2. So let's take some x1 in Rn and x2 in Rn. Then the line passing through x1 and x2 is essentially equal to theta x2 plus 1 minus theta x1. So it's essentially the set of all points that can be written as a special linear combination of x1 and x2, right? Now, if I don't restrict myself to these kinds of linear combinations, let me take, say, the set of all alpha x1 plus beta x2, and I vary alpha and beta over all possible r, then what do I get? Which is a plane. It's in general going to be a two-dimensional subspace, assuming that x1 and x1 is not equal, or x1 is not a scalar multiple of x2, right? So that's going to give me, as you said rightly, it's in general it will give me a two-dimensional object. But if I constrain the set of all linear combinations, if I say that alpha plus beta should be equal to 1, then I basically get a line. It's sometimes helpful to write this in the following form. It's the same thing. So theta x2 plus 1 minus theta x1 can be written as x1 plus theta times x2 minus x1, right? So this is, you can view this line as having a base x1. Let me call this the base, and x2 minus x1 can be viewed as a direction. Right? So essentially I take a point, call this x1, I take another point, let me call this x2, right? So I'm looking at the straight line that passes through x1 and x2. So if let's say I take theta equal to 0, what do I get? It's just x1. So for theta equal to 0, I get this point x1. If I take theta equal to 1, then what do I get? Substitute theta equal to 1 in here, I get x2, right? So as you vary theta from 0 to 1, it essentially interpolates between x1 and x2. But again, I have no other restrictions on theta except that it's a real number. So for all positive values of theta, this essentially corresponds to the line that starts from x1, goes until x2. As I increase theta beyond 1, it goes further away. Right? It's like a ray that is shooting out from x1 in the direction of x2 minus x1. And it goes on all the way up to infinity. Similarly, if I take theta negative, then it goes in the opposite direction. Right? So this direction is essentially theta greater than or equal to 0, and this direction is theta less than or equal to 0. So for negative values of theta, the direction of the line is opposite to x2 minus x1, whereas for theta positive, it is in the direction of x2 minus x1, but the ray originates at x1. All right. Okay. In fact, we can try to visualize this in 3 dimensions. So just as an exercise, let me just write a simple program to plot this line and see what happens for different values of theta. Let me take 2 arbitrary points, say x1, y1, z1, 0.1, 0.9, 1.2, x2, y2, z2. This is, let's say, 0.9, 1.2, 2. Okay. What I'm interested in is what happens as I take some combination, let's say 1 minus theta times x2, 1 minus theta times x1 plus theta times x2. So let me define theta. Let's say theta varies from minus 2 to 2 in steps of 0.01. Okay, and let me just plot this particular linear combination of x1 of these 2 vectors, right? So first I need to define a figure. I want a 3D plot, and let me plot let's say z1, theta times x2 plus 1 minus theta x1 Okay. Let me also plot x1, y1, z1 and x2, y2, z2. So I'll mark the point x1, y1, z1 maybe in black. And x2, y2, z2, maybe I'll just color this in red. Right, so you can zoom in and see this. You basically get the straight line that passes through these 2 points. So this is x1, y1, z1, and this point is x2, y2, z2. Right. So now let's also see the ray that originates from x1, y1, z1 and moves in the direction of x2 minus x1. So let me define the direction. So dx, dy, dz to be dx x2 minus x1, dy 2 minus y1, dz z2 minus z1. Right, so this is x1, y1, z1. This is x2, y2, z2. The line or the ray in the direction of x2 minus x1 originating from x1 is basically this. So now let's see what happens if I take, say, only positive, so positive values of theta, negative values of theta. Right, so instead of varying theta from -2 to +2, let me just vary it from 0 to +2. What do I get? You see that it only goes in this direction, in the direction of theta, or in the direction of this ray. Similarly, if I take only negative values of theta, let's say from -2 to 0, right? You see that the line, it's basically a ray that goes out in the direction opposite to x2 and originates from x1, the first. Likewise, if I only let theta to be between 0 and +1, then I just get this portion of the line that is between x1 and x2. So each of these will be given a special name. All right, and all of these different sets, different portions of this line segment can be obtained by further restricting the value of theta. Right, if I restrict theta to lie only between 0 and 1, then I just get this line segment. If I restrict theta to be positive, any positive value, then I essentially get a ray that originates from x1 and the direction of x2 minus x1. And if I let theta to be only negative, I get another ray but which moves in the opposite direction. Yeah. Which one? There's only one free variable, which is theta. In all of these cases, there's only one free variable, theta. I have not talked about length so far.
Yes, it will be a segment, but from my understanding of length, it extends both sides.
It does. So here so this is basically the line, right? It goes all the way from minus infinity to plus infinity. So this is the straight line that passes through these 2 points. And in this case, I let theta to vary to be any value between minus infinity to plus infinity. Okay? So it extends infinitely in both directions. But if I restrict theta to only be positive, then it extends only in one direction. If I let theta to be only negative, then it extends all the way up to infinity, but in the opposite direction. If I let theta to only vary between 0 and 1, then I just get the line segment that interpolates between the x1 and x2. Right? So this is what I'll call a line. A line segment is basically set of all x. So when I say line segment, it's a line segment that interpolates between 2 points, x1 and x2. So this is again theta x1 plus 1 minus theta x2, where theta can only take values between 0 and 1. Again, you see that if I take theta to be equal to 0, then I get, maybe I should write it in this way instead. 1 minus theta x1 plus theta x2. So if I take theta to be equal to 0, then I get x equal to x1. If I take theta to be equal to 1, then I get x equal to x2. Right? So line segment joining x1, x2. Similarly, the ray originating or with base x1 and in the direction x2 minus x1. This is basically this set x, which is equal to x1 plus theta times x2 minus x1. But now you allow theta to go all the way up to infinity, but it has to be positive. Yeah. I didn't quite get your question. So in this case, you're allowing theta to take all possible values from 0 to infinity. It's going to lie in the same line, but it's going to lie somewhere beyond x2. Right? So, for example, let's go back to this, what we plotted over here. I can plot. Okay, so this is basically the line segment, and let me also plot what happens when I take theta is equal to plus 10, right? So let me take theta is equal to 10. I'll mark this in green, right? So I'm not sure if you can see it clearly, but this is basically the line segment. This is x1, this is the point x2, and this is the theta x1 plus 1 minus theta x2 for theta equal to 10. Right? It's going to be in this direction. It's going to lie along the same straight line, but it's going to be further away. So similarly, if I just take 10, right, it's still on the same straight line. Any other questions? Okay, so why am I going through all of this difficulty in defining what a line is and a line segment is? Because we want to characterize certain classes of sets, right? So we'll begin with the notion. After all, in the end, we want to define what it means to be a convex set, right? And a convex set is just going to be a set such that if you take any 2 points, then the straight line, then the line segment that joins these 2 points should also lie within the set, right? And based on this, based on whether it contains all possible lines or line segments or rays, we classify sets into the following. So I'd say that a set is affine if it has the following property. No matter if you take any 2 points, so you are given a particular set A, we say that it is affine if no matter how you choose x1 and x2, every affine combination, or in other words, every line or the entire line that passes through x1 and x2 is contained in A. Right, so if 2 points belong to the set A, then the entire line that passes through these 2 points should also lie within A. Right? So now if I take any 2 arbitrary points, what do you think is the smallest affine set which contains these 2 points? It's the entire line that passes through these 2 points. Correct? So basically every line is therefore affine. Can you give me an example, any other example of an affine set? Line and? Okay, would this be affine? It won't, right? Because then you take this other point and any point on the line joining those two should also be within the set if it is to be affine. So now, okay, let's start with the basics. What is the smallest affine set that you can think of in Rn? Yeah, a single point. There's even something even more basic, which is the empty set, right? But okay, the smallest non-trivial set would be a single point, right? Because after all, there's only one point, and you can't really make any interesting linear combinations with just one point. The next bigger affine set that you can think of is a straight line. You take 2 points. Obviously, for the set to be affine, the entire line joining those 2 points should be in the set, which means that a straight line is an affine set. What is the next? A plane, right? You take a plane, you take any 2 points on the plane, the straight line that passes through these 2 points will obviously lie within the plane. Next, yeah, hyperplane, right? So all of these, so basically all of these sets, lines, planes, hyperplanes, are all affine sets. Are there any other kinds of affine sets that you can construct other than points, lines, planes, hyperplanes in general? Is it affine? Yeah. Circle, take any 2 points on the circle. Is a straight line joining those two within the circle? Disk. Take any 2 points within the disk. Is the entire line, again, when I say line, it extends all the way up to infinity, right? The answer is no. No matter what you do, the only affine sets are basically general hyperplanes, right? So whether you say it's an affine set or a hyperplane, it's essentially the same. Okay. We'll revisit affine sets in a little bit, but okay. So now essentially for affine sets, you take 2 points, the entire line passing through those two should also lie within the set. Let's now restrict ourselves to only line segments. Right? So A is said to be convex. If you pick any 2 points, then the line segment that joins those 2 points should also lie within the set. So if I take a set that looks, say, something like this is not convex, because if I take, let's say, a point over here and a point over here, then this entire line segment does not lie within the set. There's a third special class of sets which is called a cone. X2 in A. Now this is something that I'll define a little differently. X1 I'll first begin by defining just a cone passing through the origin. So for all x in A, theta x also lies in A for all theta greater than or equal to 0. Alright. So you take any point within this set, then the ray that originates, that starts from the origin and passes through this particular point should lie within the set. Okay. So here are some questions. Is every affine set convex? Yes, because after all, for a set to be affine, it should be closed under all possible combinations of this particular form, where theta can be any number from minus infinity to plus infinity, whereas convex sets are obtained by putting further restrictions. Only the line segment that joins 2 points should lie within the set. So yes, every affine set is convex. What about the other way around? Is every convex set affine? No, can you give me an example of a convex set which is not affine? Yeah? Okay, a filled circle. So, in fact, in general, let's take the set of all x in maybe Rn such that the norm of x, L2 norm of x is say less than or equal to 1. It's basically an n-dimensional ball. Are you convinced that this is a convex set? You can see that visually, but how do you prove that this is a convex set? You take any 2 points, okay, within the ball, okay, okay.
No, we take it on the surface.
You want to prove it for every point, every pair of points within the set.
First, we take it on the surface. Any point joining those two will be less than 1 unit away from the origin.
Why? Okay, so each of these 2 points will be 1 unit away.
The height, perpendicular height is.
Okay.
Yeah, you can show that it's closer to the origin. So
It's not enough if you say you can show that. You have to show it. Yeah.
Extension of this unit radius is to the n dimension.
I don't follow.
Extension of unit radius is in 2 dimensional to the n dimensions. So every point will be within the ball.
again, it's not a proof, right?
So that I just do theta into x plus 1 minus theta into another point, and since these two are less than 1, so
Yeah, you basically use triangle inequality, right? So take any right, what I want to do is show that this set, so let me call this B, or let's say Bn, okay? So it's not enough to just know, we should also be able to convince ourselves of each of these points, right? What I want to show is that Bn is convex, and the only thing I can rely on are the definitions that I know, right? So take any 2 points, let's say x1 and x2, which lie in Bn. And any theta between 0 and 1. What I want to show is that theta, whatever, theta x2 plus 1 minus theta x1 also lies within the bond. So let's find the 2 norm, theta x2 plus 1 minus theta x1. In fact, it doesn't matter whether this is the 2 norm or any other norm. Using this approach, you can prove that every norm ball is convex. Now this, just by triangle inequality, this is less than or equal to the 2 norm of, or the norm of theta x2 plus the norm of 1 minus theta x1 just by triangle inequality. What else do I know about the norm? What is norm of a times x? It is mod a times the norm of x. But in this case, theta and 1 minus theta are both non-negative. Mod theta times norm x2 plus mod of 1 minus theta times norm of x1, which is nothing but theta norm x2 plus 1 minus theta norm x1. But we know that both x2 and x1 lie within the ball. So what can you say about the norm of x2? It's at most 1. Similarly, the norm of x1 is also less than or equal to 1. So this is less than or equal to theta plus 1 minus theta, which is 1. So the norm of any such combination, theta x2 plus 1 minus theta x1, where theta lies between 0 and 1, this is less than or equal to 1. Right? So this, so not every convex set is affine, but every affine set is convex. What can I say about cones? Can every affine set be a cone? Is every affine set a cone? Again, we look at the definition of what a cone is very carefully. Yeah,
The point about
a single point cannot be a cone. There is one situation where a single point can be a cone. If that single point is only the origin, right? But if there's even one non-zero point, then that point cannot be a cone, right? Okay, so now is every affine set a cone? How many say yes? Every affine set is a cone. How many say not every affine set is a cone? Okay, you need to convince me one way or the other. Yes, correct. So you take any line that does not pass through the origin, right? This is not a cone because for it to be a cone, you take any point in the set, then theta times x1 should lie within the set. So in other words, you take the ray that starts from the origin and passes through this point, this entire ray should be within the set. So firstly, the origin should be a part of your set for it to be a cone. By definition, you just take theta equal to 0, right? So when is an affine set a cone? When the origin is included in the affine set, yes, but what when the origin is included in an affine set, it has a special structure. Yeah, I heard somebody say this.
one of x1 and x2.
What do you mean? One of x1 and x2 is not.
Right.
The affine set could be multi-dimensional, right? For example, if you take a plane,
Sorry, what's the question?
so the question is, if the origin is contained in an affine set, then this set has a special structure. It's a vector subspace, right? So, now if I take a single ray, right, a ray that passes that starts from the origin and goes out to infinity, yeah, is this an affine set? So let me define what I mean. Let me take some point x, say x equal to 0, 1, 2, right? And I look at the set. Let me say that A is the set of all theta times x, theta greater than or equal to 0. So this is a ray that shoots out of the origin and in the direction of x. Okay, so Fine. Convex cone. Is it affine? Is it convex? Is it a cone? Firstly, is it affine? I don't hear an overwhelming yes or no. It is not, right? Because if I take minus x, this is not contained within the set, but it should be contained if it is to be affine. So it is not affine. Is it convex? It is convex because if you take any 2 points on this ray, then the line segment between that joins these 2 points, that is contained within the set. So this is convex. It's a ray, so is it a cone? Yes. Right. But note that not every ray is a cone, because it has to contain the origin. A ray that does not pass through the origin, in fact, a ray whose base is not at the origin is not a cone by this definition. We look at more general definitions of cones when we can think of it as a shifted version of a cone. Why is it called a cone? Yeah, so so what do you think of when I say cone? Basically your ice cream cone, right? So let's take that very specific example. So how do you define the ice cream cone? It's basically it's the set of all let me say x comma x prime in Rn plus 1. So I look at the ice cream cone in Rn plus 1. So these are basically vectors of length n plus 1. I'm going to denote this sort of special way. We'll see why in a moment, such that x prime is less than or equal to norm x. I'm sorry, this should be greater than or equal. Let's see what happens in 3 dimensions, because or let's even take 2 dimensions first. N plus 1 is equal to 2. Okay. So in 2 dimensions, this is the set of all x1, x2 in R2 such that x2 is greater than or equal to mod x1. Okay, let's plot this. Let's assume that this is my x1 axis, this is my x2 axis, right? What does x2 equal to mod x1 look like? Basically this, right? Correct. What is the set of all what is the set of all x1, x2 such that x2 is greater than or equal to mod x1? It is this entire region which is above the curve x2 equal to mod x1. Correct. So this is basically my set. Right. Okay. Let's try to see what happens in 3 dimensions. So this is the set of all x1, x2, x3 in R3 such that x3, we want, let's write this as xyz, such that z is greater than or equal to square root of x square plus y square. Okay. Again, let's try to visualize this in 3 dimensions. So what does x square plus y square look like? X square plus y square equal to a constant is basically a circle, right? Or square root of x square plus y square equal to a constant is basically a circle, right? And we're looking at the set of all z for which x square plus z, which is greater than or equal to x square plus y square, right? So what will that look like? Yep, so basically you think of circles, you keep expanding the radius and you go up, right? Which is basically a cone. Right? So if you fix a particular z, right? Another way to look at it is you fix a particular z and you look at the set of all x comma y such that x square plus or square root of x square plus y square is less than or equal to z. What is that? That's a circle, right? It's the entire circular region which gives you this for a given z. So you keep varying z from 0 all the way up to infinity. What happens? You keep getting a series of growing circles. Right, and this will just give you the ice cream cone, but of course it extends all the way up to infinity. Now, is this a cone by our definition? Which one? I mean, so okay. I'm calling this a cone, but let's say that this is our set. Okay, we don't know whether this is a cone or not yet. So this is the geometrically, when you think of a cone, this is what the first thing that comes into our mind, right? So is this actually a cone according to our definition? Why? Well, geometrically, if you take any point within this cone, right? You take any point inside this cone, then the ray that shoots out and passes through this will also be within this cone, right? That's intuition, but the intuition is not enough. So let's take any x, y, z, right? Or more generally, right? So this is my definition. Right, so take any x prime that lies in this set. What I want to show is that any theta times this should also lie within the set, right? So take theta, say y prime is equal to theta x prime for some theta greater than or equal to 0. Does y prime satisfy this? It does, because so y prime, let me look at y prime divided by norm y, assuming that this is non-zero. This is equal to theta x prime divided by theta norm x, which is greater than or equal to 1, as x prime belongs to a set. All right. So if some vector lies in the set, then theta times that vector for every theta greater than or equal to 0 also lies within the set. So it's a cone. So all of this is helpful if geometry and intuition is helpful if you're in Rn, because in this case I could, just by looking at it, geometrically thinking about what the ice cream cone is, you can convince yourself that yes, it's indeed a cone. You take any ray that starts from the origin, that will also be within this ice cream cone. But let's look at something that is more interesting. So let's take the A is the set of all n by n positive semi-definite matrices. So firstly, is this affine? Yes, no? If yes, you have to tell me yes. If no, then you have to give me a reason as to why it is not. Yeah? So if it is affine, you have to prove that it is affine using just the definition. If it is not affine, then you have to give me at least one x1, x2 and a theta for which x1 and x2 are PSD matrices, but some theta x1 plus 1 minus theta x2 is not a PSD matrix. Yes, can you give me an example? So let's take any non-zero PSD matrix. Okay, let's call that X2. Okay, let's take one PSD matrix X2 which is non-zero, right? And let me take X1 to be equal to the zero matrix, all zeros matrix. Is the all zeros matrix PSD? People are not convinced. What are the eigenvalues of the zero matrix? All zeros. Are all of the eigenvalues non-negative? Yes, right? So the all zeros matrix is PSD, correct? And let me take any other PSD matrix X2, which is non-zero. Okay. Can I construct some theta X2 plus 1 minus theta X1 such that this is not PSD? Can you give me one value of theta for which this cannot be PSD? Okay, give me one value of, yep, take minus 1. Theta equal to minus 1. This is obviously, this just becomes minus X2, right? If X is a non-zero PSD matrix, then can minus X also be PSD? It can't. Why? Yep, so one way is to say that X, if you look at, say, Y transpose X2 Y is going to be less than 0 for some Y. I'm sorry, this is greater than 0 for some Y, which means that Y transpose minus X2 Y is less than 0 . So minus X2 is not PSD. So it's not affine. What about convex? Yes, it is convex. And why? Okay, so
Yes, is not.
okay,
Then theta x1 minus theta x2. They apply y transpose that matrix into
theta x2 y, this is nothing but theta times y transpose x1 y plus 1 minus theta times y transpose x2 y. This is greater than or equal to 0 because x1 is PSD. This is greater than or equal to 0 because x2 is PSD. So this combination is also greater than or equal to 0 because both theta and 1 minus theta are greater than or equal to 0. Is it a cone? It is a cone because again, to take any theta times x y transpose theta xy is theta times y transpose xy, which is greater than or equal to 0 if x is PSD and theta is greater than or equal to 0. Right? So beyond just cones in Rn, you can also come up with these other types of cones like the set of PSD matrices. So similarly, you can think about whether the set of positive definite matrices is affine, is it convex, is it a cone? What do you think? Why is it not a cone? Yeah, theta equal to 0. So so the set of positive definite matrices is not a cone. Is it convex? It turns out that yes, it is convex. Right? And another homework is every cone convex? Right? I want you to think about it. Any questions so far? Any questions? Okay, so in that case, we'll have a quick quiz. Please keep all written material away. So no more than 3 in a way. Did everybody get the sheet? Please write your name and roll number.